Okay, so once again, back to this problem we just worked on a minute ago, but these are just really tricky because you got two things going on. You got metal and water. So back to our initial issue. For the metal, we don't know the Q and we don't know the C, so we can't solve it because we're missing two variables. So here's what we can do. We know a lot of information about the water. So if I go ahead and talk about the water, if I talk about how much heat we can determine from the water, the nice thing is that the Q of the water and the Q of the metal are the same. It's just they're going in opposite directions. So the water is going to be heating up, the metal is going to be cooling down, and then we can use that information to figure out the Q, which is the same for both. It's just in opposite directions. The amount of heat gained or lost is the same. One gained it, one lost it. So let's do the Q of the water. And I usually just write H2O, so I probably should just do that. So there's the H2O. And that's going to equal the mass of the water. This is where students always have trouble because there's a lot of data here. You just got to look at it. So see, this is the water data, 20 grams of water. So let's put that here for M. So 20. There's the 20 grams of water. Okay. And then the specific heat. Well, we talked about this in the notes already, but the specific heat for water is always the same value. Okay. And so the specific heat of water is going to be 4.180 joules, and it's always the same. So this is not given to us because 4.180, that is always the same for water. So they're never going to give it to you because you gotta look it up or remember it. But this is water's value. And then change in temperature. Okay, same thing. Using these two data points over here. So we're using these two data points right there. Final minus initial. So we're going to go final 22.03 minus initial 18.51. So let's do that on our calculator. 22.03, because remember, the final temperature is the same for the metal and the water because you dump the metal in, they equalize out, not a big deal. So I'm going to get 3.52, and we're going to go ahead and drop that in right here. I'm going to kind of try and squeeze that in there. There we go. And let's go ahead and just draw an arrow right there so you can see how we got that. And now we can solve this, right? So we can get Q. So let's solve this. So we're going to take 20 times 4.18. And I got my calculator out right now. You should be doing the same thing. Times the 3.52. Okay, can't read my own writing. And I get a Q value of 294.272. So let's use 3 sig figs. So let's say that the Q of the water equals 294. But here's the problem. Remember what I said. Whatever happens to the water, the metal or the reaction, which in this case is the metal, is doing the opposite. So the metal is not absorbing energy. The plus 294 is from the water. So what we do is we say, okay, the Q of the metal then is going to equal negative 294. It heats up. Things that heat up get things that are giving off heat, heating up the water. The water got warmer. It is heating up. And so we need to logically say, okay, I understand that the Q should be negative. All right. Now, if we're honest, this is one of the hardest problems on the test for students because they got to juggle multiple things. So now that you have a Q right here, well, that Q that you have, 294, will go here. And using the rest of that, we'll be able to get a final answer. Okay, so we find a space to work. And so I'm going to switch back over to the red. So let's sneak it in here. So this is, oh, don't want that. So let's go Q of the metal equals, okay. Sorry, messed that up. So the Q of the metal, we already know the equals. I just need to write it in. So negative 294. I don't have a lot of space for fooling about. Now Q is actually measured in joules here. So it's probably best to put that right there. Not a big deal mathematically, but and so the mass right here, 10.25. X is what we're going to solve for. And negative 77.07. Okay, now, when we're solving for this, there's a lot of little steps, but this is going to get us the answer. This is going to give us our X, which is going to be our C value. So our C values are not particularly large usually, so we should not get one that's particularly large, and we should get a positive one. So if you look at this, a negative and a negative, so we've got a negative and a negative, then we are going to get a positive, and we're going to be set up. So let's solve for X. Okay, so the way you're going to solve for X is we're going to take the negative 294. We're going to divide it by, in parentheses, 10.25 times negative 77.07. A little bit of algebra. Close the parentheses, and then get your answer. Okay, I got 0.373 sig figs, so 0.372. That's what you should get. Now, if you're not getting that, it's really just an algebra issue at this point. So I'm going to have to find a place to put this answer. So let's write this answer in yellow. And so then our final answer, so maybe I'll just clean this bit up right here. You guys hopefully have that written down. So let me clean that bit up here, and then I'm going to write our final answer is going to be C of the metal equals 0.372. Now it makes sense that it's a lot less than, it's a significant amount less than the water. And so that should make sense to us because water has a pretty high value, metals have a pretty low value. And so this is our final answer right there. Hard problem. Okay, but guys, test question. Talked about it. We're going to be ready for the test. We're going to know how to do this one. Okay. This one is not near as hard because this one is not using all kinds of different issues you got to mess around with. So I'm going to walk you through this one and let you try it. So we've got a gram value for lead. We have a temperature value for lead. That's initial. They want to know a new temperature after the lead absorbs this much heat from its surroundings, and there's a specific heat. What I wanted you to notice here, that there's no mention of water. They're not talking about water. All the data is about the lead. There's only one chemical here, so you can only solve it one time. So we can only do Q of the lead equals the mass of the lead times the specific heat of the lead multiplied by the change in temperature of the lead. So you don't have options this time. So this is actually a significantly easier problem. So you're really just dumping in a bunch of numbers and doing a little bit of algebra, and you're going to get a temperature value. Now here's the trick. It's going to give you a change in temperature. Okay, your X value is a change in temperature. It's not your final answer, it's a change in temperature. So you'll have to look at how it compares to this 22.5. Okay, so you're going to try that, and then I'll work that here in a minute. Okay, so you guys should have paused it. You guys should have gone through and solved this one or attempted to. So let's go ahead and switch the pen over to the different color. So let's put in our mass. So 454 is going to go here. So 454 grams. So drop that in here. Initial temperature is not going to be used yet because we're going to use that at the end. Okay, because we're finding change in temperature. So specific heat, 0.128. This is our X, so we're looking for a change in temperature. Not a final temperature, but a change in temperature. So it's we have to do a little work with it. And then right here, 4.22 kilojoules of heat. Now that's a problem. And hopefully you spotted it, but you may not have. Here's the issue. This value, and you can see it right here, is in joules. And this is kilojoules. They're not going to play nice to each other. You're going to have to do some manipulating in order for those to work. All right, so what we're going to do is it's a lot easier to change this value here than to change that value there. All right, so what we're going to do is we're going to take our kilojoules and we're going to quickly convert them into joules. So you're going to take your 4.22 kilojoules and you're going to do a quick little conversion. And so I'm going to move it down here because I don't have space. 4.22 kilojoules. And you're like, okay, I want joules. I don't want the kilojoules. 1 joule is equal to 1,000 kilojoules. Sorry, 1 joule is equal to 1,000 joules is equal to 1 kilojoule. So if you have your conversion factor set up correctly like this, kilojoules are going to cancel. And so you're just simply multiplying by 1,000. So bump the decimal 3 spots. This is going to get replaced with 4,220 joules. So now your units are going to play nice. Now, might have missed that, might have had a smaller value there, but that's really just understanding your units. Okay, so let's solve this for X, which is not a final answer, but a change. So you're going to take 4,220 divided by, in parentheses, 454 times 0.128, close your parentheses, hit enter, and you're going to get, because of sig figs, we're going to go with 70, I got 72.6. So this is going to equal delta T equals 72.6. That is not your final answer. You're going to have to go ahead and look at this and say, okay, it's positive, which means that my temperature should have been going up. So what we're going to do is we're going to take this number, 22.5, which is where we started. We're going to add 72.6, which is where we're going. And then that is going to create a new temperature. So we're going to add that up. So I just went to the 3 sig figs on the 72.6. So 72.6 and 22.5. And your temperature of your lead after you do all of this stuff is going to be 95.1 degrees Celsius. So maybe you didn't get that, but hopefully you had parts of it. And then once again, you kind of see how this works. This is another very good test question. And so you do need to know how to do both varieties because they both come up. So, put a star by it, put a happy face by it, get yourself ready to go.